Hello, everyone, and welcome back to another Teach Astronomy stream. How you guys doing today? I see we've got a couple people already in the chat. Welcome, Barry and Mahika. How you guys doing this morning? Everyone else who hasn't chatted yet on this lovely Monday morning. Here in LA, it's sunny as always, but it's getting colder, so I've got myself some tea. I always have a Starbucks cup. I'm like not that crazy about Starbucks. It's just like I always have the cup. Like they gave me a free cup the other day and I was like, well, I don't want to spill everything all over my computer, so I'll use a closed mug. But I've got myself some tea and I'm ready to read. It's a little bit warmer in my house today. You said it was a good day. That's good. I'm glad. Yeah, I'm sure it's not morning for everyone, but I hope whatever part of the day you're in right now, or maybe you're not even in Monday. There are definitely some people that are already in Tuesday, right? Time zones confuse me, but I hope you're having a good one. And thank you for joining me. So if you have been here before, you know that we're reading Einstein's Monsters. It's a book by Professor Prof Impey. He's kind of the flagship of this channel sort of thing. And it's a book about black holes and the history of them, their discovery, black hole theory, stuff like that, but made for people who aren't astrophysicists like myself. Also, disclaimer at the beginning, I'm not an astrophysicist or astronomer myself. I do not have any sort of degree in that. I'm kind of the Twitch expert of our group, but I've worked with an astronomy group for 3 years now? 4 years? It's been a few years. 3 years? I think it's 3 years. So I know a lot of the basics. I've taken some of the college classes, but so I can answer some of your questions, but a lot of the stuff we kind of learned together. So yeah. So right now we're actually last week we finished part A, so we're going to be starting with part B today. So it's called Black Holes: Past, Present, and Future. So yeah, I guess if we're all set, if everybody's got their hot or cold beverage of choice and is ready to start reading, I guess we can just start going. Also, I have a new mic now, so hopefully it sounds a little better. Let me know if I'm too quiet or too loud, and I can adjust my volume there. Also, if you guys haven't been here for a little while, hi Adam Altogether, how you doing? If you guys haven't been here for a little while, I think Adam Altogether knows this, but we've got a fun little alert box now. So if you guys put in bits or like follow or subscribe or anything, your name will come up. It'll make a fun noise and stuff like that. So if you feel like doing that. All right. So I guess I'll start from the beginning, of this section. What is the life story of black holes? Astronomers speculate that some black holes may have been created soon after the Big Bang, when the infant universe was hot and dense. Since then, small black holes have formed as massive stars die, and large ones have grown by guzzling gas at the centers of galaxies and by combining when galaxies merge. In the second part of this book, we look at how black holes of different sizes are formed and grow. Now that their existence is no longer in doubt, astronomers are designing observations to probe closer and closer to the event horizon. Researchers have also learned how to explore the properties of black holes within the safety of a computer simulation. Black holes are the ultimate proving ground for the theory of gravity. They allow us to put general relativity to the test as never before. Most of the excitement in black hole research in the next decade will come from the detection of gravitational waves, ripples in space-time that are a central prediction of general relativity. When black hole mergers were first detected a few years ago, a new field of astrophysics was launched. Gravity wave detectors will soon be able to detect black hole mergers across the observable universe, with an event every week. If humans survive that long, our distant descendants will be treated to a close-up view of the merger of the black hole in our galactic center with a similar black hole in the Andromeda Galaxy. We close by looking at how black holes grow and are eventually starved as the universe expands and galaxies dissipate. Even the largest black holes will one day evaporate in a whisper of Hawking radiation. Nothing lasts forever. Not the universe, and not black holes. Oh, you're not late, Selva. It's okay. Also, good morning, Falas Bear. That was just the intro section for section 2. So you didn't miss anything. It's just essentially Chris saying what's going to be coming. So don't worry. It was just like a page. No worries at all. It's so nice to have people hanging out. All right, so now we did the little intro section. We're going to be starting on chapter 5, which is the lives of black holes. The universe contains black holes ranging from city-sized objects with the mass of a star to solar system-sized objects with the mass of a galaxy. How are black holes born, and how do they live their lives? The story starts with the Big Bang and continues with violent star death and mass convergence at the centers of galaxies. With a mixture of observation, theory, computer simulations, and a dose of speculation, astronomers have pieced together the history of black holes. They have even considered the question of whether the universe itself is a black hole. Seeds of the universe. The early universe was chaotic and unstructured. Although the universe had been getting lumpier as gravity forms planets, stars, and galaxies, it was never perfectly smooth. Just after the Big Bang, there were slight non-uniformities, and since the average density of the universe was extremely high, gravity in these regions would have been very strong. The seeds for the formation of galaxies thus date back to the early universe, but that's not all. In the same year he predicted the radiation that bears his name, Stephen Hawking and his student Bernard Carr wrote a paper about black holes that may have formed in the very early universe, primordial black holes. They argued that even if the density variations that occurred just after the Big Bang were small on average, variations in some regions could have been large enough to create a gravitational attraction that exceeded the force of cosmic expansion. In those locations, gravitational collapse would occur and a black hole could form. This process can make black holes of almost any mass. Could Hawking's primordial black holes have been the seeds of the universe? The earliest black holes would have been formed at Planck time, the period 10 to the negative 43rd seconds after the Big Bang, when the universe was 10 to the negative 35 meters across. It's very, very, very small. Black holes that formed then would have had a mass of 10 to the negative 8 kilograms, and about that of a mote of dust. These early black holes couldn't grow due to the rapid expansion of the universe, and thus quickly evaporated. Any black hole that formed less than 10 to the negative 23rd seconds after the Big Bang with a mass less than 10 to the 12th kilograms would have evaporated by now. But later forming and more massive ones might survive to the present day. A primordial black hole that formed a second after the Big Bang would have had a mass of at least 100,000 solar masses, not far short of the Milky Way central massive black hole. Another intriguing theory holds that primordial black holes might persist in an unexpected form. For the last 40 years, astronomers have been dealing with the problem of dark matter. Stars and galaxies of all kinds move too quickly to be explained by the gravity of the stars themselves. There seems to be an extra component of mass, 5 or 6 times more than the sum of all the stars, that's holding galaxies together. This dark matter exerts gravity, but it doesn't emit light or interact with radiation in any way. Gravitational lensing data shows that dark matter also fills the space between galaxies. What if dark matter was made of primordial black holes? It's an attractive possibility. In theory, primordial black holes, like dark matter, should be found throughout the cosmos, and positing them as a source of dark matter avoids invoking a new fundamental particle that's outside standard physics and hasn't yet been seen by accelerators. Unfortunately, careful observations have eliminated most of the ways primordial black holes might exist, including as dark matter. When a black hole evaporates, it releases a torrent of gamma rays. By the 1980s, NASA had gamma ray detection satellites in orbit, but they didn't see the expected signature. Gravitational lensing rules out widely distributed black holes from galaxy mass down to Earth mass. Recent theoretical work has closed the door on the last mass window, from 10 to the 14th to 10 to the 21st kilograms, or from the total carbon mass in the atmosphere of the Earth up to the mass of a small solar system moon. Primordial black holes can't be abundant enough to account for dark matter, but that doesn't mean they don't exist in some form. They're predicted by cosmological theory and have the potential to illuminate our understanding of the early universe. The search continues. And that's that section. I'm going to put that down for a sec. I have a question for you guys. Just a fun little question to chit chat about. So we've been reading a book about black holes that is very much a nonfiction, scientific. I guess this is just categorized as like a science book. I barely read nonfiction, so I don't even know how they categorize them. But speaking of that, I was wondering what you guys are reading, or what your favorite genres are, or what you're listening to, if you guys prefer audiobooks and stuff like this. I'd just love to know, because right now, besides this with you guys, I'm reading a fantasy novel series the first one's called Three Dark Crowns. It's so good. I'm on the second book now. It's excellent. And I also just read Scavenge the Stars. That was also very good. That's another fantasy. I think it's fantasy. There's like magic mentioned, I think. I think it's fantasy. And that's typically what I go for, is sci-fi fantasy stuff. And I was wondering what you guys like. So let me know, and I'll start reading this next section. First light and first darkness. Just a few seconds after the Big Bang, conditions no longer favored the formation of primordial black holes. The universe at that moment was an almost perfectly smooth cauldron of high-energy particles and photons, with density variations of less than 0.001% from one place to another. A few minutes after the Big Bang, the temperature had dropped to the point where atomic nuclei could form. Fusion converted a quarter of the mass of the universe from hydrogen to helium, with trace amounts of lithium and isotopes of hydrogen and helium. This took no longer than the time needed to boil an egg. The temperature was 10 million degrees. You'd need X-ray vision to see the universe then. The universe continued to expand and cool. The next important milestone occurred at about 50,000 years, when the energy densities of matter and radiation were equal. Thereafter, the energy density of radiation fell more rapidly than matter density as photons were redshifted by expansion. As a result, gravity exerted its grip, and the tiny density variations could start to grow. The temperature of the universe was 10,000 degrees. If there had been anyone there to see it, it would have been glowing blue. About 400,000 years after the Big Bang, the temperature had fallen to 3,000 degrees, and electrons joined nuclei to form stable atoms. Radiation traveled freely for the first time. The red fog lifted, and nascent structures came into view. It was still early days. Compared to an age of 13.8 billion years, 400,000 years is the blink of an eye, the equivalent of the first 10 hours of a 40-year-old human life. As it expanded, the universe faded from view. Its radiation slid from dull red to invisible infrared. This was the beginning of the Dark Ages. The Dark Ages continued until the first stars and galaxies formed, 100 million years or so after the Big Bang. So this entire era lives within the first 1% of the age of the universe. Intriguingly, although the first fraction of the lifetime of the universe was dark, it might not have been lifeless. From 10 to 20 million years after the Big Bang, the universe had a temperature between the boiling point and the freezing point of water. The present-day universe is extremely cold, and biology as we know it can only exist in slender habitable zones near stars, or perhaps in colder locations under the surface of a planet or moon where water is kept liquid by pressure from above and radioactive heating from below. But there was a time when the entire universe had a habitable temperature. What isn't clear is whether or not the rare early stars could have made enough carbon for biology to develop, and enough heavy elements to form a planet for that biology to inhabit. It's also doubtful if 20 million years is enough time for life to evolve from simple chemical ingredients. Some of the most important questions in cosmology center on the Dark Ages. When did it end? Which formed first, stars or galaxies? How were the formation processes affected by the absence of heavy... Oh, gosh. Sorry. How were the formation processes affected by the absence of heavy elements? What's the best way to detect first light in the universe? And most important for our narrative, what kind of black holes were first to form? I'm going to pause there for a sec. If two photons collide in space, what would be the effect? I don't know. Let's find out together. Again, like I said, I'm not the PhD holder in this group, you know. But photons collide in space. Let's see what they say on Chrome. The billiard dynamics of photon collisions. We're going to take a little detour right now. It seems like they're trying to figure out what it does. Photons can interact with each other through quantum processes. So there would be some sort of interaction, it seems like. But it's extremely hard to see. Will they annihilate? Maybe? I don't know, actually. It seems like they're just saying that the process could be observed right now, but obviously, it's really hard to observe the process. And that the probability of it is extremely low, but it's not non-zero. It is non-zero. It might release a particle-antiparticle pair. It's very interesting. That's more of a question I would say for it's a tough question to answer, but that's more of a question for for Professor Impey, the one who wrote the book. He actually does a what's it called? Astronomy Q&A every week, where we switch between here and our YouTube channel. And he is an extremely smart man and has been doing work in astronomy and astrophysics for the last I don't want to date him, but at least 40 years, I think. And he could probably give you a lot better of an answer to that question. Oh my gosh, the AutoMod held Atom Altogether's message because of Philip K. Dick's name. Which is very funny. Let's see what you say. When you're not reading about astronomy, you also like reading sci-fi and science fantasy. Oh, space opera. That sounds fun. And do androids dream of electric sheep? Yeah, that's the one that inspired, oh my gosh, the Blade Runner, right? I think that's the Blade Runner book. It's another sci-fi, but it inspired a big sci-fi film. It is Blade Runner. Okay, yeah, cool. And then Charlie, I like Bossa Nova, said, as for book reading, you skip around. I wonder if there are antimatter photons. Probably. I don't know. I don't have the best grasp on what antimatter is. Photons are their own antimatter particle, right? I don't know. These are a lot of good questions. I wish I could answer them better. I wish I had the degree to allow me to answer them, unfortunately. I could tell you anything you want to know about how to light a scene for film and how to structure a movie. Yeah, of course. I love reading Chris's book. It's really interesting because I get to read as well. Or I get to read as well, yes, but I get to learn as well, too. Speaking of which, I will get back to that. All right. Let's assume for a moment that dark matter is a new type of fundamental particle predicted by theories that unify three of the forces of nature. As an ingredient in cosmology, dark matter is fairly simple. It exerts gravity but doesn't interact with light or any other form of radiation. There's 6 times more dark matter than normal matter, so it dictates the formation of structure in the universe. As dark matter is concentrated by gravity, small or low-mass clumps begin to emerge. The first structures... Sorry, I lost my my section for a second. The first structures to form 100 million years after the Big Bang, as the Dark Ages ended, have 10 to the 6 solar masses of dark matter. That's the mass of a tiny dwarf galaxy in the present-day universe. As time passes, these clumps merge to form bigger and bigger clumps. Each clump of dark matter contains a puddle of normal matter, 1/6 the mass of the dark matter, and that gas collapses into the center of the dark matter gravity pit. When it collapses, stars form and first light is triggered. In this bottom-up scenario, small objects form before large objects. Stars form before galaxies. And we have a figure for this. So let me show that to you. So this is a figure. Goes along with what I just read. So the description under it says, a 2-dimensional representation of the evolution of the universe from the Big Bang 13.7 billion years ago. The exponential early expansion gives way to slower expansion. The universe is dark from 400,000 years to a few hundred million years after the Big Bang, when the first stars and black holes form. Massive black holes grow due to galaxies merging and gas falling into galaxies. In the last 5 billion years, expansion has accelerated due to dark energy. So you can see, so it's essentially like a timeline. So this is where the Big Bang first started, back on this side. This is kind of where we are now. And then you can see that the Dark Ages section here, so there's that like afterglow light, right? And then there's the Dark Ages where it's really dark, and then all the stars start to form, and the black holes and the planets and the galaxies and all that stuff, and continues out. And then you can see it kind of gets bigger as it goes. It's expanding. Cool. It's awesome that I know how to light a scene. Yeah, it's I know that. I'm my specialties, my areas of expertise are like screenwriting and sound design and sound recording. There's a better word for it. Sound mixing on set. I did a lot of that in college, and I still do a lot of screenwriting and stuff, but yeah, I know how to light a scene. I know how to work a camera, fancy ones, stuff like that. Photons don't have charge, so no antiparticle as far as we know. Oh, okay. Yeah, and because an antiparticle has opposite charge to a particle, yeah. And so if photons don't have one, then don't have a charge, then they wouldn't have an equivalent that has the opposite charge. That makes sense. Very interesting. Thank you for that. All right. The universe was very different as the Dark Ages ended and the first lights flickered on. It was 30 times smaller, 30 times hotter, and 330,000 times denser than it is now. The other major difference was the lack of elements heavier than hydrogen or helium. The process of star formation depends on heat being radiated away so that gravity can make the gas cloud collapse. Carbon and oxygen have spectral transitions that very efficiently carry away energy. The lack of these elements in the early universe means that star-forming clouds were hotter and more massive. In the local and current universe, the upper limit of star mass is about 100 times the mass of the sun. In the early universe, the first stars probably ranged up to 200 to 300 times the mass of the sun. Long ago, million solar mass clumps of dark matter formed stars that on average were dozens of times more massive than the stars forming now in the neighborhood of the sun. The lives of the first stars were short. They raced through their nuclear fuel in a few million years. In computer simulations, the most massive stars explode as supernovae, leaving nothing behind, or they collapse directly into black holes 20 to 100 times the mass of the sun. Like the first stars themselves, the black holes they leave behind are more massive than the black holes we find nearby in the Milky Way. Everything you've read is based on theory and computer simulations. What about the observational search for first light? There are two approaches, and they're both like searching for a needle in a haystack, since the first stars are scarce, and the universe has been forming stars steadily for 14 billion years. One approach is to look for stars in the Milky Way that are made of only hydrogen and helium, which would mean they formed from gas that had not been polluted by any previous generation of stars. In 2012, a group at the European Southern Observatory followed up a faint star from the Sloan Digital Sky Survey and found that it had a heavy element abundance 200,000 times less than the sun. At 13 billion years old, it's the best candidate for a primordial star. The other approach is to find stars without heavy elements in a distant galaxy. In 2015, another European group saw pristine stars in a galaxy at a redshift of Z equals 6.6, meaning the light dates from less than a billion years after the Big Bang. David Sobral of the University of Lisbon, the lead author, named the galaxy CR7 for Cosmos Redshift 7, but also for his favorite soccer player, Cristiano Ronaldo. Sobral said, "It doesn't really get any more exciting than this. This is the first direct evidence of the stars that ultimately allowed us all to be here by fabricating heavy elements and changing the composition of the universe." That's the end of that section. Particle-antiparticle annihilation is valid only if the total charge is conserved. Since photons have no charge, they can be their own antiparticles. That makes sense as well. I appreciate you guys coming in here and like being very smart about those more complicated questions. You guys are all very, I'm sure you all have your own science backgrounds and stuff, which is why you're here, you know? I think that's why everyone finds Chris is they have some sort of connection with science and astronomy and physics or something, and they want to learn more, and you know, then they find the rest of the channel and hang out and stuff. And it's really cool. All right. Oh, also just a quick note, because it seems like there's a good amount of you guys here right now. We talked about this on during Chris's live stream last Thursday, but we are doing a little subscriber Christmas giveaway thing. So Chris has a bunch of books, obviously. We're reading them. And he has some copies of those books back in his office in Tucson. And we wanted to send out one of those books to one of our subscribers who wins this little contest. So we're going to do a little raffle. So if you are subscribed to the channel by, actually it's tomorrow, by the end of the day tomorrow, and we'll do end of the day for like everyone, which is, what's the last time zone? Does that make sense? The IDLW time zone? Oh, yeah, in the International Dateline. Okay. What time is it there? It's 6 a.m.? Okay. I think. I hope that's right. But we'll do it at whatever their midnight is. So at the very end of the 15th. So by the very end of tomorrow, whenever that is, probably like 3 or 4 in the morning for me, I think. I'll or 6 in the morning. I don't know. Just do it if you want to do it like today or like tomorrow. But we are going to be doing a little giveaway. So if you subscribe by then, you will be entered into a raffle to pick a book that Chris will sign for you. One of his books, obviously. But you get a signed book from Chris. We'll ship it to you. It'll be a little Christmas present and a thank you for subscribing. And so every subscriber gets an entry into that. And then also every bit donor, which I don't know if you guys can see that, but the top 3 bit donors are, there's in the stream chat, there's a thing where it says like, gift us up now to be number 1. And if you hit the arrow, it'll say who, so right now Ace's Hammer and Adam all together are the 2 that are in the lead for bits. So whoever are those top 3 for the month will get amazing. Thank you for the map of time zones. Oh, that's really cool. Time zones are wild, but they're very interesting to me. Yeah. So right by the international date line is where I'm talking about. That's cool. Which means that, yeah, it's like 4 hours behind me. But yeah, so if you want to do that, make sure to subscribe or to cheer some bits, and we will get you into that little raffle. Also, a reminder that if you have Prime, it's free to subscribe. You just have to link your Prime accounts. And if anyone is interested in that, let me know. I made a little video and I can link you guys to it. But if not, I won't crowd the chat. But we will continue. Black hole birth by stellar cataclysm. In July 1967, 2 American Vela satellites detected gamma-ray pulses. A Cold War invention, these satellites had been launched to detect Soviet violations of the 1963 Nuclear Test Ban Treaty. The public didn't know at the time, but the U.S. government was in a heightened state of preparedness for war. Luckily, a team from Los Alamos National Laboratory showed that the gamma-ray flashes were unlike the signature of a nuclear weapon, and deduced that the sources were located far beyond the solar system. In 1973, this discovery was declassified and published as a research paper. Yet, the mystery deepened. There was one gamma-ray burst every day somewhere in the sky. For a few seconds, these sources outshone the entire rest of the universe in gamma rays. But they also faded quickly, lasting from a few milliseconds to about 30 seconds. The positions measured by gamma-ray satellites were too crude to allow follow-up of the bursts, and the distribution was random, so it gave no clue to their origin. The breakthrough came in the late 1990s, when a rapid response X-ray satellite started taking data in orbit. It could quickly pivot to catch lower energy X-rays from the gamma-ray event, and accurate X-ray positions allowed optical astronomers to catch the fading afterglow. Spectroscopy showed that the objects responsible for the bursts were in distant galaxies, billions of light years from the Earth. The large distances meant that the bursts must be phenomenally bright. One event in 2008 would have been visible to the naked eye for 30 seconds, despite occurring halfway across the universe. The light that appeared briefly in 2008 was emitted 3 billion years before the Earth formed. Another burst that was seen in 2009 was in a galaxy at a redshift of Z equals 8.2. So that event occurred when the universe was just 4% of its present age. The strongest bursts put out 1,000 times more energy than a supernova, up to 10 to the 44th joules. That's the lifetime energy output of the sun, emitted in a second rather than spread over 10 billion years. When a gamma-ray burst goes off, catching the optical afterglow is the only way to measure redshift and luminosity, which can help tell us how old an object is and point us toward how massive it might be. A few years ago, I was on the 6.5-meter multiple mirror telescope on Mount Hopkins in Arizona when I got an internet alert. NASA's SWIFT satellite had detected a gamma-ray burst, and the call went around the world to take a spectrum. It was 3 a.m., but I set aside my coffee. Nothing wakes you up like chasing a stellar cataclysm. Within minutes, we were at a... Oh, thank you for the cheer, virtual assistant. All right. Sorry, I stopped in the middle of the sentence. If you want to get my attention, you cheer. And then, oh, please link it. Okay. Let me finish this sentence and then I will do that. It was 3 a.m., but I set aside my coffee. Nothing wakes you up like chasing a stellar cataclysm. Within minutes, we were at the position. Nothing was visible on the TV monitor, so we worked blind and hoped for a signal. The next day, the reduced data showed a ragged trace with hints of emission lines, but they weren't strong enough to measure a redshift. The following night, it had faded beyond detection. In astronomy, sometimes you have to settle for the thrill of the chase. That's not the end of the section. I'm just going to link you guys that video real quick. Yeah, I know that a lot of people were a little confused by how the linking of Twitch and Prime works. And, like, you get a whole free subscription to whatever channel you want with Prime. So, like, I want to make sure people know how to do it, you know? So, where is that video? There it is. Okay. Get a shareable link, please. So that should be the video. Let me know if it doesn't link you to the right thing for some reason. But yeah, it's short. If you guys want to go do that now, feel free. If you want to do it later, also fine. During one of my little chit-chatty breaks, you can do it if you don't want to miss reading stuff or just like open it in another window. But it only takes a minute. Essentially, you just have to be logged into your Twitch, which you probably already are if you're chatting, and your Amazon. Go to the right website, it'll link them for you, and then you come back here, and then you'll have the option under the subscribe tab to do the free subscription. So yeah, I would really appreciate that if you guys did it, because you know, this is just a channel we do because we want to. So hopefully we'll be getting a new grant eventually, but right now we're just doing this because we care about, you know, astronomy education, and I like doing Twitch and stuff. But anyway, while you guys do that, I'm going to continue. Astronomers believe gamma ray bursts are the calling card of a newly formed black hole. The thousands of events studied so far divide into two populations: high luminosity long duration events and low luminosity short duration events. The most luminous bursts are due to the collapse of the rotating core of a massive star, typically more than 30 times the sun's mass, which forms a black hole. Matter near the star core rains down onto the black hole and swirls into an accretion disk. The falling gas creates twin jets along the rotation axis, which travel at 99.99% of the speed of light and pound their way through the star's surface to radiate as gamma rays. Much of the gravitational energy is released in the form of neutrinos rather than photons. Oh, and we have a figure for that. Let's grab that. That's the old figure. Hold on. We want this one. There we go. So this says, the violent birth of a black hole can be marked by a burst of gamma rays. As energy emerges in relativistic jets along the polar axis of the black hole spin, a blast wave creates extremely high energy electromagnetic radiation. For a few seconds, such explosions are the brightest objects of the universe in gamma rays, detected at distances of billions of light years. So you can see here, lost my mouse for a second. You can see here the black hole engine, and then it says low energy gamma rays, faster shell, slower shell. Colliding shells emit low energy gamma rays, so there's the internal shock wave, and then here's all the different kinds of electromagnetic radiation it releases in the afterglow. Very, very cool. All right. Also, if I go too fast with any of those figures, let me know, and I can pull them back up. Okay. The quicker bursts are thought to be caused by the merger of two neutron stars, or the merger of a neutron star and a black hole. Either of these cases results in a single black hole. Most of the energy of the merger is released in the form of gravitation radiation. space-time ripples that radiate outward at the speed of light, as predicted by general relativity. Matter falling into the newly formed black hole forms an accretion disk and releases a burst of energy. A hypernova is an even more extreme type of black hole formation event. It releases hundreds to thousands of times more energy than the normal death of a massive star in a supernova. That's not nice. Somebody just sent a very not nice message. Don't appreciate it. We don't like not nice people here, do we? I blocked it so you guys don't have to see it, but I had to see it, and that upset me. I'm sorry. It distracted me. I'm going to start that section over again. A hypernova is an even more extreme type of black hole formation event. It releases hundreds to thousands of times more energy than the normal death of a massive star in a supernova. The record holder is an explosion reported in 2016 that was 500 billion times brighter than the sun. Imagine 20 times more light than all the stars in the Milky Way, crammed into a space 10 miles across. This explosion was the biggest recorded since the Big Bang, a mind-boggling fact that challenges any physical theory of the energy it released. Such an enormous explosion raises an uncomfortable question. Is the Earth at risk from a stellar cataclysm? In other words, though we don't have to worry about falling into a black hole, should we worry about a black hole reaching out to smack us? The good news is that these events are rare, about 1 per galaxy per million years. Also, the radiation is concentrated in twin beams, and the explosions are randomly oriented in space, so 99.5% of them will miss us. That takes the average incidence down to 1 per galaxy per 200 million years. The bad news is that if we happen to be in the line of fire and the blast is within a few thousand light years, the Earth and its biosphere will get hammered by high-energy radiation. Gamma rays would deplete the ozone layer by 75%, spiking mutation rates. The total effect on the ecosystem is difficult to estimate, but one group argues that the late Ordovician mass extinction 450 million years ago was caused by a gamma ray burst. The evidence from the extinction is considered consistent with ozone depletion and a loss of surface species, but there's no way astronomers can pinpoint an explosion that ancient because the black hole is all that's left. There's more impressive evidence that a milder event occurred within recorded history. In 774 AD, the Western world was a patchwork quilt of small warring states. Charlemagne was consolidating his kingdom with conquests of Tuscany and Corsica. In Japan, where Buddhism was rapidly becoming the state religion, Empress Koken had 1 million prayer scrolls made. They're almost the oldest printed works in the world. Among the oldest, Carbon dating shows that the trees that were felled to create these scrolls had experienced a sharp increase in their carbon-14 to carbon-12 ratio. This spike is Exhibit A in making the case that the Earth was irradiated by a gamma ray burst about 1,250 years ago. Carbon-14 is radioactive and decays into nitrogen. The fact that it exists at all is due to cosmic rays, high-energy particles from space, hitting nitrogen in the atmosphere. This process maintains a constant low level of carbon-14, but a spike by a factor of 10, as observed in the scrolls, must have had an additional external cause. Exhibit B is a rise in carbon-14 in trees in Europe and America, although the date is harder to pin down. Exhibit C is a small jump in radioactive beryllium-10 around that time. Beryllium-10 is created when high-energy particles hit an exposed surface. Its concentration is used to date glacial advances, lava flows, and other geological events in rocks as old as 30 million years. None of this can be explained by a solar flare. Nor can it be explained by a supernova, because any supernova that close would have been visible in the daytime sky, and none was recorded in medieval manuscripts. That leaves a gamma ray burst. At a distance of about 5,000 light years, it would have dumped 200 megatons of gamma ray energy into the Earth's atmosphere. The afterglow only lasted a few days or so. So even though it would have been visible to the naked eye, it's likely that nobody noticed it or thought to record it. Meanwhile, astronomers have their eye on a massive star called WR 104, which is 8,000 light years away and likely to die with a violent core collapse sometime in the next few 100,000 years. We cannot measure its orientation in space, so when it goes off, we'll have to hope that one of its powerful jets isn't pointing in our direction. Astronomical timekeeping is crude enough that this timescale isn't completely reassuring. It may go off much sooner. In the meantime, there are better things to lose sleep over. And that's that section. Give me 1 second. I just have to check something here. Hope everyone's doing well today. Sorry for the silence for a second. Oh no. I opened my moderator view and apparently the desktop audio is silenced anyway. I was afraid you guys heard me echoing by accident because my mod view sound was on. Sorry, I like the Einstein. Also, hello, Vodka Wazaki. Welcome to the chat. Thanks for hanging out. If you guys are new, it seems like we got a few new viewers in the last 10 minutes or so. We're reading a book called Einstein's Monsters. It's about black holes, and it's by my boss. I keep holding it the wrong way. There we go. Einstein's Monsters. It's about black holes, and it's by my boss, Professor Prof Impey. So, yeah, we're having a good time talking about black holes. And guess we can just keep on going. Oh, actually, just saw that from Astro Kiriani. I hope I'm saying your name right. I missed the last discussion about the lunar descent when discussing space news. By any chance, can you discuss that again next time? Yeah, we can do that for sure. I don't know what we're planning on doing this Wednesday. I know. So Michael, if you guys haven't tuned in to our Wednesday streams, me and my co-host Michael do every other week we do astronomy news talks, and then the other weeks we do some sort of focus on a certain something or other, and different we've had a guest on that talked about exoplanets, stuff like that. I'm sorry, I got distracted by Mad Lad's message. That's hilarious. He got his teeth cleaned and he's enjoying the existential dread of a potential galactic cataclysm. I feel that, man. Yeah, these books by Chris are fun to read, but they're also yes, and the world will blow up one day, and it's cool. Really excited about that. But yeah, we can totally discuss that next time, about the lunar descent and stuff. Because yeah, like I was saying, this week, I know Michael's not going to be able to be on the whole time, because he's got finals, but I am not a student anymore, which is great. So I can do whatever I want. But he'll be joining me at least for the announcement of who won that book drawing. So again, if you guys are new, if you subscribe, or if you are one of the top 3 bit donor people, cheerers, by tomorrow night, by the end of the 15th, you will be entered into a book drawing. Student McLeod said, are we looking for ideas for shows? Absolutely. We are always looking for recommendations and ideas for different streams. So please, if you guys have any ideas, it could be fun streams, because we do some of our gaming streams once a month. It could be regular stuff. Please let me know. Feel free to throw that in the chat if you guys have any recommendations for fun streams that you'd like to see on the channel, or fun topics that you want me to cover. You'll share one towards the end of the session. Okay, thank you. I'm going to write these down really quick, though, so I don't forget. So we'll talk about the lunar landing. And I'm assuming you're talking about the Chinese lunar lander, right? And the Martian spacecraft descent? Yeah, sure, we can talk about that. I actually don't know which one that is, but I will look it up. And what does space look like from the ISS? That's a fun question. I like that. And Starship SN8. Okay. I don't know what all of these are, but I will by Wednesday. I'll do my research. And then what does space look like from the ISS? That's cool. I'm going to find some photos for you. And we'll get to chat about that. Want to become famous? Buy followers, primes, and viewers. Get out of here. Ugh, I hate these people. I mean, they're not people, they're bots, but they're so annoying. Oh, thank you. You're awesome, Charlie. All right. We will continue. Yeah, feel free to keep making those suggestions. If the chat gets too crowded, I'll make sure to go back up. But if you got suggestions for shows or topics about anything, really. Also about amateur astronomy stuff, because we're not doing one this week, but... and then we have a guest at some point in January, but we're always looking for ideas for that stuff too. Okay. Where was I? Is the real question. Where was I? Oh no. Oh, it's Vicky with a Y, by the way, if you were curious. I mean, my real name is Victoria, but everyone calls me Vicky, so and we're all chill. We're all hanging out here with a Y. I totally forgot where I was. I'm trying to look back in the chat to see. Oh, I finished the section. I did finish the section. Yeah, because I said there are better things to listen. I just got so confused. Okay. I feel bad for anyone who's listening to this afterwards because I archive these on YouTube. I'm so sorry that I go off on these tangents and get confused, but I hope you're enjoying this anyway. Those are for the future listeners. Okay. Finding the missing links. We've talked about two different kinds of black holes. One forms from the death of a massive star, when a star that started its life at between 8 and 100 times the mass of the sun leaves behind a dark object between 3 and 50 times the mass of the sun. The other forms at the center of a galaxy and ranges from a few million times the mass of the sun in non-active spiral galaxies such as the Milky Way, up to a few billion times the mass of the sun in giant elliptical galaxies such as M87. That leaves a huge gap in mass, 5 powers of 10, from a few dozen solar masses up to a few million. Do intermediate mass black holes exist? A small set of objects have been found that push into the gap from the low end. Recall that Arthur Eddington worked out the limit of the brightness of a black hole. The faster black holes eat, the brighter they shine. But even if a black hole is feasting on plentiful gas from a companion in a binary system, there's a limit to its brightness. The pressure of radiation blazing off the accretion disk counteracts the black hole's gravitational pull. So at some point, excess gas trying to fall in is blasted back into space. That's called the Eddington limit. 30 years ago, a rare class of ultraluminous X-ray sources, ULXs, was discovered. They pump out 1,000,000 times more X-ray energy than the sun's total power, and they're bright enough to be seen in galaxies millions of light years away. According to the Eddington limit, these black holes must be hundreds or thousands of times more massive than the sun. Slap bang in the middle of the mass gap. Luminous X-ray binaries are important for another reason. Some are scaled-down versions of quasars. The exotic binary system SS433 is 18,000 light-years away, in the constellation of Aquila. A bloated blue star orbits a black hole every 13 days, and siphons gas onto the accretion disk around the black hole. Some hot gas falls into the black hole, while the rest is funneled into twin jets that shoot out along the rotation axis of the black hole. The gas moves at a quarter of the speed of light, covering a mile in 20 microseconds. SS433 is the archetypal microquasar. Oh, we have a figure. Let's see. So here's our figure. So this is a figure showing SS433. So it's the binary star system with an early type star and a black hole. So this is a visualization since the system can't be seen in detail from how far away it is. And it essentially is just showing how we've got the black hole here. We've got the jets coming out in the accretion disk, and it's siphoning off that gas from its companion star. So that's the accretion stream. There's a hot spot where the gas is entering this accretion disk. There's disk wind. It's a little hard to see, but this is all kind of shaded around a little bit lighter. That's like the disk wind, they're saying, and the X-ray heating. Again, it's a little tough to see. These are just like pictures of pictures in books. But, oh, and there's an illustration of Aquila. Thank you. Let's look at that for a sec. So, student McLeod, is it McLeod or McLeod? Let me know. I want to say it right. But there's the constellation they were talking about. So it is, I don't think it actually says where it is in here. At least not that I can see, but it's somewhere in this constellation. I mean, it probably says somewhere where it is. It just doesn't say it in the book. But anyway, I will continue. Microquasars have all the ingredients of a quasar: spinning black hole, accretion disk, intense high energy radiation, relativistic jets, but are scaled down by a factor of 1,000,000. There are only 100 known microquasars in the Milky Way, but they're very helpful in modeling and understanding the extreme astrophysics of quasars. The fueling timescale for a quasar is far longer than a human lifetime, while for a microquasar, it's a few hours, so it's easily observable. I feel like I'm fumbling over my words a little. What about pushing down into the gap from the high end? Let's return to a central insight of the past few decades. Every galaxy has a heart of darkness. Quasars and active galaxies are rare. The central black holes in most galaxies are inactive most of the time, so they can only be detected by their influence on the stars near the center of the galaxy. As astronomers gathered more data on black holes in nearby galaxies, they saw a striking correlation. The mass of an inactive central black hole is accurately predicted by the velocity spread, the range of motions that indicates total mass, of the old stars in a galaxy. This correlation is puzzling. These black holes only affect the very central regions of a galaxy, and stars in the galaxy outweigh them by a factor of 500. Why are these disparate quantities related? Astronomers aren't sure, but the correlation has recently been extended down to dwarf galaxies and even globular clusters with black holes of a few thousand solar masses. We have another figure, so I'll flip to that really quick. Nope, that's not the right one. There we go. So this is a black hole to, this is the black hole mass. This is just a graph of black hole mass versus stellar system mass. These are both in solar masses. So it's just showing that the stellar systems that these black holes are in, as they get larger, the black holes in the center of their galaxies are also going to get larger. So you see, we got globular cluster M15 over here, then G1. So yeah, just essentially saying they both increase pretty equally. The Scottish pronunciation of MacLeod is MacLeod, but no real Scot spells the name with the word cloud in the spelling. Those are the fake MacLeods that are never invited to the family reunions. That's funny. I like that. Okay. So it's MacLeod. All right. I just wanted to make sure I was saying it right. Thank you for that. All right. Let's continue. Elliptical galaxies are large and made up almost entirely of old stars, so they have the most massive black holes. Spirals, like the spirals like the Milky Way have fewer older stars, mostly gathered in small central bulges, so they harbor more modest black holes. Observation of smaller black holes is challenging and pushes telescopes and detectors to their limits. The best targets are globular clusters, the spherical clouds of stars that orbit the halos of large galaxies. With a few 100,000 to a few million stars, the correlation described above predicts black holes of several thousand solar masses. Detections have been claimed, but none has survived skeptical scrutiny. Nonetheless, a handful of objects have filled in the gap. In 2012, for example, a 20,000 solar mass black hole was seen in the dwarf galaxy ESO 243-29, and in 2015, a 50,000 solar mass black hole was found in the dwarf galaxy RGG 118. The most significant discovery of an intermediate black hole came late in 2015, when Japanese radio astronomers spotted a swirling gas cloud only 200 light-years from the center of the Milky Way. They tracked the rotation with spectral lines from 18 different molecules and deduced the presence of a dark object 100,000 times the mass of the Sun. The discovery supports the idea that black holes grow the same way aggressive companies do, by mergers and acquisitions. I was not expecting that. Millions of years from now, when the 4 million solar mass black hole at the center of our galaxy consumes this intermediate creature, the central beast will grow by 2.5%, and we can imagine it emitting a burp of satisfaction. This burp will be registered as a pulse of high-energy radiation hitting the Earth 27,000 years later. And that's the end of that section. Oh, and we have a photo of M15. Thank you. So this is one of the... Student McLeod is just killing it with these images. But this is one of the galaxies that was mentioned in that section. This is a globular cluster galaxy. And so at the center of it is a black hole. And this is one of the smaller ones that they're able to detect and to visualize. Yeah, or not to visualize, to study, I guess. Yes, Student McLeod is my wingman, one might say. I really appreciate it. He's always getting me some photos and cool stuff. Single coded, how you doing? Welcome to the party. I don't know if you've been here for the whole time, but for what you pay me, I need to send him pictures. Do I pay you? Because that's news to me. I pay you in reading and knowledge, what I can provide. All right. Just checking to see. You know, I feel like these sections are all getting longer. Checks in the mail for sure. I feel like all these sections are getting longer. They're not. I checked this morning. They're all like exactly 30 pages. I don't know how Chris did that. It's very impressive to me. But like every chapter is exactly like 30 pages. I just get tired quicker, I guess, when I do these now. My voice gets tired quicker. My tea is cold now, but I'm going to keep drinking it because it's good tea. All right. So, something with the number 30. Oh, something with the number. I was like, what are you talking about? No, I was just saying that every chapter is like 30 pages. If he has something with the number 30, if there's a significance, I don't know. It's just very impressive. Like maybe it's different for like nonfiction books and stuff, but like, I mean, I write, and every chapter I write is going to be like a wildly different length. All right. So, simulating extreme gravity in a computer. Einstein thought about gravity in an entirely new way. Gravity was not, as Newton posited, pulling or tugging objects around in space. An object moving in response to gravity was following the shortest path, called a geodesic, through curved space-time. An astronaut slowly falling toward a spacecraft is simply following the curvature of space-time. The moon circles the Earth because the shortest path through space-time brings it back to the same point in space. A two-dimensional version of this happens every time you take a long plane flight. Imagine flying from Los Angeles. Hey, that's where I live. So imagine flying from where I live to Madrid. Even though these cities are at the same latitude, the plane doesn't fly due east. It heads north and flies over the southern tip of Greenland before heading south. It follows the shortest distance between those 2 points, as you could confirm if you stretched a string over the surface of a globe. The pilot doesn't need to turn left or right. The route is a straight line on a curved two-dimensional surface. Everybody's chit-chat. The simplest form of general relativity is written as g equals 8 pi t, where g is the space-time curvature at a point and t is the mass at that point. Technically, it's mass energy, but since energy only has a tiny amount of equivalent mass according to E equals mc squared, for astronomy situations it works to just consider the mass. This little equation applies at all points in space and encapsulates everything we need to know about gravity. However, this elegant equation is the highly compact form. It's useless for solving any real problems. To apply general relativity to something like a black hole, the full expressions have to be used, which expand into 10 different equations, each with many terms. To solve these equations involves a fiendish amount of difficult algebra and calculus. And to understand what happens when two black holes of different masses merge, every term in every one of Einstein's equations has to be used. Written out, it's 100 pages of dense math. No simplification is possible. In the 1990s, after rapid mathematical and computational advances, numerical relativity took off. Approximations to Einstein's equations were developed. They centered on methods to separate space and time, sampling the space so finely that Euclidean geometry could apply. Computation uses an adaptive mesh where the space grid is coarse where gravity is weak and flat, and fine where gravity is strong and curved. The grid is adjusted continuously as the situation evolves. Computer speed is measured in floating point operations per second, or flops. That's funny. An IBM 7090 computer, which was state-of-the-art in 1962, had a speed of 100,000 flops. In 1993, I just find the word flop so funny as an acronym in science. That's hilarious. In 1993, the fastest computer was 1,000,000 times faster. Now it's 1,000,000 times faster still, or a staggering 10 to the 18 flops. The National Science Foundation spurred this research with grand challenge grants to simulate a binary black hole collision. The numerical work turned up some surprises. Such a merger can produce an enormous amount of gravitational radiation, 8% of the total mass of black holes. Also, when two black holes merge, the resulting black hole can get a kick speed of 400,000 miles per hour, enough to eject it from any galaxy. Let's use a canvas as a visual metaphor for something that can't be seen, space-time. The canvas is painted with gravity. So far, we have just stretched the canvas of empty space-time. There's a figure with this. I'll show you guys this as I read it. So this is our canvas. General relativity is a geometric theory of gravity. So if there's mass anywhere, the space-time canvas is curved, and it can contain punctures and tears and folds. The canvas is three-dimensional, so impossible to visualize. But the canvas isn't the whole story. A black hole in the real universe is surrounded by radiation and hot gas, and high-energy particles and magnetic fields. And underneath this figure it says, numerical relativity is the field of solving Einstein's gravity equations by computational methods, in a complex and realistic astrophysical setting where exact solutions to the equations are impossible. One requirement is to work at different size scales. So for a binary black hole, this ranges from the orbital scale to the event horizon scale. And as illustrated here, one powerful method is called adaptive mesh, where the sampling of space-time in the calculations automatically adjusts to the strength of the local gravity. So you can see, so I guess this isn't really a canvas that he mentioned, but it's got it's hard to see, but these are essentially like caving into the page, you know? They're like visualizations of black holes that are bending space-time down. Oh my god, you found a picture of Professor Impey's home in space in Edinburgh? Not in space. He doesn't have a house in space. That'd be wild. I don't know if I'm supposed... Oh my god, wait, that's hilarious. You're very funny. So this is his house. This is a joke. I'm pretty sure this is a castle. Or something. What is this? What is this place? It doesn't say. Is this is this the school or something? You gotta tell me where that's from. That's hilarious. I was like, how did you find his house? That'd be crazy. I thought you were gonna have like his address. You see him waving from window. Oh, it's the Edinburgh Castle. Okay. My partner actually went to Edinburgh for his first couple years in undergrad, and now I really want to go because it looks freaking beautiful because they've got stuff like this castle. Look at that. It's amazing. Yeah, you should, I mean, if you can, you should totally study there. They've got a really good program. A lot of really good programs. I don't know if you want to do like astronomy and physics stuff, but whatever you want to do. It's beautiful area. Also very haunted if you're into that. I know that's like controversial since we're in a science talk, but I don't know if they have a specific astrophysics program. I know a lot of schools break astronomy and physics, and then like at University of Arizona, they have astronomy, they have physics, and most people that study astronomy will also study physics. They'll have a second degree in physics. Some programs just do astrophysics. I'm not sure. Something to look into. I like the little Illuminati thing. That's fun. Yeah, Edinburgh is beautiful though. I mean, I haven't been, but I really want to go. I've seen a lot of pictures. Okay. We were after the canvas thing. There we go. Okay. We're talking about 3 levels of difficulty. Level 1 is complex interactions between particles and radiation. Level 2 adds in magnetic fields. Level 3 includes gravity. At this point, researchers are exploring a technique called general relativistic magnetohydronomics, which is a real conversation stopper at cocktail parties. I really talk about it. To use a game analogy, the 3 levels are as checkers is to chess is to Go. In this spectrum of technical ability, I'm nifty at checkers. I can hold my own at chess, but I'm completely flummoxed by Go. The full numerical treatment aims to represent the complex astrophysics of not just the black hole, but also the accretion disk and the twin jets. This is the state of the art in black hole simulation. Fewer than 100 people in the world have the technical skills to do this work. Computers can simulate small black holes, but what about the large ones that live at the centers of galaxies? For this, we meet Simon David Manton White, Fellow of the Royal Society and Director of the Max Planck Institute for Astrophysics in Garching. He's a magician with gravity in a computer, so we'll dub him the Sorcerer. The Sorcerer has sad eyes, a tidy mustache, and a graying mop of curly hair. He looks weary, but you'd be weary too if you made the universe from scratch. The Sorcerer studied for his PhD in Cambridge with Donald Lyndon Bell, black hole pioneer and visionary. He has over 400 refereed publications and more than 100,000 citations, eye-blinking numbers that place him in the rarefied stratosphere of his subject. He's a world He's a world expert on the properties of dark matter and on the formation of structure in the universe. Here's how you make the universe in a computer. Set up a three-dimensional grid of space. Add normal matter and dark matter in the correct proportions. Switch on gravity. Make the space expand according to the Big Bang model, and watch a filigree of large-scale structures congeal from the initially smooth distribution of mass. A large number of particles stand in for astronomical objects. For example, 1 million particles might be used to represent a star cluster with 1 particle per star. But no simulation has enough particles to represent a galaxy with 1 particle per star, or the universe with 1 particle per galaxy. So in practice, a particle represents a varying amount of mass. As an analogy, imagine using 1 million particles to model human populations. In a model of the world, each particle would represent 7,500 people, or the number of people living in a village or a small rural region. No finer detail is possible. But the same model could represent the gory details, with 1 particle per person, for a small state in the US like Rhode Island, or a moderate-sized city like Austin, Texas. The computational demands rise rapidly as the number of particles increases, so White and other programming gurus use tricks to speed up a simulation dramatically. After all, nobody wants to wait 13.8 billion years for the outcome. White's simulation was known as the Millennium Run because it was the first powerful mock-up of a large chunk of the universe after the year 2000. These simulations only include gravity. But galaxies have gas as well as stars, and gas behaves differently from stars. When 2 spiral galaxies collide, the stars and the dark matter particles almost never collide, so those components of the galaxies pass through each other. But the gas components crash into one another, heat up, glow brightly, and form stars. Gas behaves more like a fluid than a set of particles. To deal with the gas, the simulators mimic gas behavior with smoothed out particles that have a probability distribution instead of a single location. They also layer in physics via equations to include important but small-scale details like supernova explosions and black hole formation. Listen to Simon White talk about his landmark cosmological simulation. This is all in quotes. What was novel in the original Millennium Run was first of all the overall size, which was roughly a factor of 10 larger than previous calculations. And also the fact that we implemented techniques which allowed us to follow the actual formation of visible galaxies in a rough but physically based manner. We were able to predict not only the distribution of the unseen dark matter component of the universe, but also where the things we can actually see should be and what their properties should be. There already have been surprises. One was the realization that to understand the properties of the visible galaxies, we must understand the effects of the black holes in their centers. The actual population of galaxies was shaped by the development of the black holes in their cores. It is not true that the small object in the center is divorced from the rest of the galaxy, even though the black holes only contain 0.1% of the stellar mass of the galaxy, a very tiny fraction. End quote. The Millennium Run was completed in 2005. It used 10 billion particles to simulate a cube of the universe 2 billion light-years on a side. The results required 25 terabytes of storage. That's not the whole universe, but it's large enough to be a fair sample that encompasses the largest structures gravity can form in 14 billion years. Hundreds of scientific papers have been published based on the simulation. The current state of the art is the illustrious simulation. Following Moore's law, the gain in computing power that results from transistors getting smaller, the size of the best simulation doubles every 20 months. By the end of 2017, the simulators had cracked the trillion particle barrier. With Illustrious, for the first time, it's possible to realistically model a substantial fraction of the universe down to a level of detail that can resolve the structure of an individual galaxy. A computer can now track the fueling and growth of millions of supermassive black holes across 13 billion years. Like many theorists in astronomy, Simon White's initial training was in mathematics. He recalls weighing his choices for graduate school. Quote, "I had 2 options in Cambridge. One was to do theoretical fluid mechanics, aerodynamics, and this kind of thing. There, the students were in the building, in the center of Cambridge, in basement offices with no windows. The other option was astrophysics. The Astrophysics Center was outside the town, and it was a building with a lot of windows. There also were trees and cows across the road. I thought astrophysics looked a little better. End quote. And that's the end of that section. Mad Lad said someone's going to the wrong kind of cocktail parties. Oh, that's funny. Referencing, I think, that comment before where Professor Impey said if you brought that up at a cocktail party, it would probably end your conversation. That's funny. All right. It's that time of the stream when my throat starts to hurt, but I'm going to keep on going. I think we only have actually like less than 10 pages left in this chapter. I feel like I had another question for you guys. Sorry, that really threw me off. But I just realized the credit. I just noticed the credit line on that picture you shared, and one of their last names is also my last name. That's weird. Crazy stuff, you know? Small world. I just love that picture of the castle. I've just got that up on my other screen. It's very nice. Okay. I'm going to keep going. How black holes and galaxies grow. The lives of black holes and galaxies are intertwined. A supermassive black hole occupies a tiny fraction of the volume of a galaxy, and it has a tiny fraction of the galaxy's mass. Yet we've seen that every galaxy has a black hole, and the mass of the black hole is tightly coupled to the mass of the stars in the entire galaxy. What does that imply about how black holes and galaxies grow together over cosmic time? The glory days of quasars are long gone. We can detect supermassive black holes lurking in nearby galaxies, but they are mostly quiet, like the black hole in our own galaxy. 1 in 100 is mildly active, and 1 in a million is a quasar. Surveys at optical and X-ray wavelengths can track the brightness of quasars going back in time. The peak of quasars occurred at redshifts of Z equals 2 to 3, about 11 billion years ago, or 2 to 3 billion years after the Big Bang. They were thousands of times more active than they are now. The ancient night sky was quite different from our night sky. The universe was 4 times smaller, and galaxies were merging and forming stars rapidly. Hundreds of galaxies would have been visible to the naked eye, as opposed to the 3 we can see now. And the nearest quasar would have been 100 times closer, also visible to the naked eye. Observations tell the story of a rapid rise in quasar activity, followed by a slow decline. All large galaxies have supermassive black holes, but it doesn't follow that they all show quasar activity. How do we know that quasar activity is episodic rather than a property of a particular set of galaxies? Answering this question is hard, because astronomers can't stare at particular galaxies to see how they evolve. They do surveys that capture a large number of galaxies at all epochs, and use that data to take a snapshot of the activity at a particular epoch. This has been my research area for the past decade. The goal is to understand how black holes and galaxies grow and intersect with one another. I enjoy astronomy research because it hasn't gone the way of physics, with collaborations 1,000 strong and instruments that take a decade to build. It's still possible to go to the telescope for a few nights with a graduate student and a good idea and make an impact. That was how Jonathan Trump and I came to be in the foothills of the Andes, watching the sky darken over the watching the sky darken over the Cordillera and preparing our observing list. We were aiming for the sweet spot of black hole growth, the time between 3 and 10 billion years after the Big Bang, when galaxies did most of their merging and black holes did most of their feeding. In particular, we were trying to identify the lower boundary to nuclear activity. how feeble could the accretion rate be for the black hole to light up as a quasar? We managed to find black holes 10 billion light years away that were as quiescent as the black hole in the center of our galaxy. At our disposal was technology that obliterated the photographic plates I'd used in Australia 30 years earlier. Not only could we discover 300 quasars in a good night, but we could measure their black hole masses as well. John was energetic, keep stumbling over my words. I'm going to take a quick break. Oh yeah, I should try to find a guest speaker to talk about astrophysics simulations. I think that stuff is really, really cool. I know Chris knows some about that stuff, but I mean, he probably knows a lot about that stuff, honestly. But his time is very limited. That's why we were actually intending to have a special stream for subscribers. I mean, everyone can watch the stream, but only subscribers can chat in it and ask questions. We were going to do a special stream just asking Chris about like particularly like astronomy related topics. So just like about him and his like the things that he's done in his life, the cool stuff, because he's got a million crazy stories of stuff that he's done. But we were going to do it in December, and he just does not have time because he's got a million other things he's working on. But we're going to do it in January. But I should ask him if he's got people that he would know that would be willing to talk about that stuff, because astrophysics simulations are really, really interesting. Geminid meteor shower is also a good topic. I am going to your clan's castle. Ooh, I want to look at that. So actually, this is I mean, I'm gonna be like sharing something that is not related to TeachAstronomy, which bad. But like, okay, so one of our former student workers, Aiden Gibbs, he was on a few weeks ago to talk about exoplanet research and stuff. He is actually I heard he's doing a planetarium show, like a virtual planetarium show tonight with UCLA. Let me see if I can find that link. I'll actually have him send it to me. Let me message him, because he's talking all about Geminid meteor shower and like how to watch it and amateur astronomy and stuff like that. And I've seen a couple of their groups presentations before, and they're really good. Let me see if I can get that link from him. All right. We'll see if he responds in time. And we're going to look at your castle. Wait, so a clan, that's like your family line essentially, right? I think. Oh, that's cool. Let's zoom in. Oh my gosh. That's beautiful. That is so cool. Oh my god. Have you been there? That looks amazing. Wow. That's really cool. It's smaller than Chris's. That's really, really cool. I love the architecture from like that age, I guess medieval, Middle Ages, stuff like that, maybe earlier, but castle architecture is very cool. Oh great, he sent me the link. Let's see. So yeah, it looks like it's going live, and it says 7 hours for me, so at 7 p.m. Come on over, plenty of room. All right, so here's that link for that show tonight. It's going to be on YouTube. 7 p.m. Pacific time. So that'll be 10 o'clock Eastern. It's a little late, but it's California based. So cocktail party. Cocktail party at the castle. Talk about astronomy stuff. But yeah, check that out if you want to hear about Geminids, because like we can talk about it too. But they're also a really good resource for stuff. They've got good shows. So yeah, anyway, we will continue this. Tell him Teach Astronomy sent you. Because I want to see if anyone shows up. Don't call scotch scotch. Okay. It's whiskey. Gotcha. All right. So, John was the energetic apprentice, while I was the grizzled veteran. But in practice, we often switched roles. Time hadn't dulled my enthusiasm for research, and occasionally I made blunders in my haste to gather data, while he reined in my excesses and kept a steady hand on the tiller of the telescope. We hit a patch of clouds in the middle of one night, so I tried to be patient. The photons had traveled for billions of years to be captured by our big glass. What difference would a few more hours make? I walked outside and watched the sky clear. To the west were cloud tops all the way out to the Pacific Ocean. To the east, the star field was etched by the jagged silhouette of the Andes. A condor wheeled silently overhead. The last night on the telescope was tinged with exhaustion and sadness. We were treated to a green flash as the sun set. Astronomers are lucky if they get half a dozen nights on a big telescope in a year. If it's cloudy, they have to come back again next year. After this run on the telescope, we and it would part company. We puzzled over scatter plots of our data. Some quasars had hefty black holes but were sputtering feebly. Others had puny black holes but were blazing brightly. The fueling mechanism was enigmatic. We bagged 500 black holes in a week, but that felt like a pinprick in the universe with 100 billion galaxies, each harboring a black hole. Ooh. Sorry. I tried to not cough, and it didn't go well. Pardon me. Where were we? There we go. The black holes seemed to silently mock us, and they held their secrets close. We've seen earlier that sustaining quasar-level brightness requires an accretion rate of a few solar masses per year. There are two implications from such a modest fueling rate. First, there isn't much gas in the central regions of most galaxies, and black holes rarely swallow stars whole, so that fuel is exhausted in under 100 million years. Gas drizzles onto galaxies from intergalactic space, and gas is added when galaxies merge. But both processes are inefficient now that the universe is large and galaxies are widely separated. Since black hole fuel is used up much more quickly than the time taken for the observed quasar population to rise and fall, individual quasars must be on a small fraction of the time and off a large fraction of the time. Second, the modest growth rate of black holes means they shouldn't get very big very fast. But they do. The Sloan Digital Sky Survey has been looking for quasars within the first few billion years after the Big Bang. The oldest quasar it has found so far is a luminous quasar at a redshift of Z equals 7.5. This suggests that supermassive black holes, several billion times the mass of the Sun, formed and grew during the first billion years after the Big Bang. That seems to be at odds with a slow, methodical progression from small to large galaxies by mergers. It's also at odds with the maximum rate a black hole can grow as defined by Arthur Eddington a century ago. It's not possible to start with a seed mass of 10 solar masses, typical of the black hole left behind when a massive star dies, and get to a billion solar masses in a billion years. To form these ancient, luminous quasars, the seed mass must have been 10,000 solar masses. Recent simulations have suggested an explanation. In the first wave of galaxy formation a few 100 million years after the Big Bang, background radiation initially stopped stars from forming. When they did, formation was a rapid, violent process that left behind many small black holes. And in the high-density environment, those small black holes merged to form black hole seeds of 10 to the 4th to 10 to the 6th solar masses. Jump-starting black hole growth in this way enables growth to a supermassive level, a billion solar masses or more, in another 500 million years. The concept of feedback helps tie these observations together. A black hole has a symbiotic relationship with its galaxy host. It can't grow or light up like a quasar without a gas supply from the central regions of the galaxy. But when it is active, it puts out so much energy that it drives away gas in the central regions and suppresses star formation. In an active phase of 10 million years, a quasar emits 10 to the 53rd joules of energy. That's roughly the same as the gravitational energy that binds stars in their orbits of a large galaxy. So a quasar clearly has the power to disrupt a galaxy. Feedback means quasars drive out gas and quench their own activity. The gas has to build up again and start a new active phase. Feedback ties together the evolution of the inner region of a galaxy and its central black hole, and so explains the correlation that astronomers see between black hole mass and the mass of stars distributed on much larger scales. I'm going to take a drink of water real quick. This is a long section. All right. So, to put it all together, galaxies and black holes entered an intense construction phase during the first few billion years after the Big Bang. Governed by dark matter, galaxies grew hierarchically. Hierarchically? It just sounds funny. So small things formed first and merged over time to form big things. Star formation and the merger rate peaked and then went into a slow decline as the gas supply ebbed and the universe got larger. The black hole construction project went differently. The deepest gravitational potentials formed the biggest galaxies and the most massive black holes quickly. They're around us now as elliptical galaxies, long ago starved of gas, with dead quasars lurking in their centers. Meanwhile, the shallower gravitational potentials formed mid-sized galaxies such as the Milky Way, which grew smaller black holes that continued growing and staying active longer. The halcyon days of galaxy and black hole creation are long over. In the future twilight of the universe, when the last stars are dying and few new stars are replacing them, the only excitement will come from those rare occasions when two mature galaxies collide and their massive black holes merge. And we have a figure. So, not that one, this one. So this is a little flow chart about galaxy formation and evolution. So it's like it's a loop, essentially, right? So it says, there's a complex interplay between black holes and their surrounding galaxies. Galaxies grow hierarchically, going from small to large by mergers, and the activity can drive an outflow of gas that quenches the activity. Oh, nope. I skipped a line, sorry. Galaxies grow hierarchically, going from small to large by mergers, and the central black hole also grows by a combination of merging and gas falling in. Then quasar activity can drive an outflow of gas that quenches the activity, which is the feedback phenomenon. And then finally, when gas is exhausted or feedback is very strong, the black hole is starved and the galaxy hosts a dead quasar. So you see how it can, it's a flow of states and actions, and it all loops together. Sorry, I was just reading your guys' comments. Some Scottish elixir. Send it on over. I think it is kind of like the question of like which came first, chicken or the egg, because it is like a loop. So there, it's like, I guess there's it probably starts somewhere around that like growth of supermassive black holes part, because there has to be some sort of like kick that starts it, but then after that it just continues, I think. Is our supermassive black hole a dead quasar? I don't believe so. I don't think so. Picture of us hitting Andromeda Galaxy. Okay, sure, why not? That looks so cool. Okay, so Student McLeod found a cool visualization of, this is a still image, right? It has like a little play button, but I think it's a still image of our two galaxies merging. So since we can see the Milky Way here, and I'm assuming that's Andromeda because this looks more like, I don't know if you guys can actually see my curve. There we go. This seems like it would be the Milky Way. That's Andromeda as the two merge. Yeah, it's obviously photoshopped, but it's a fun little visualization. My favorite thing about the merge of the galaxies is that like a lot of pop culture is like, oh yes, and when they merge everything will explode and it'll be blah, blah, blah. And then like astronomers are like, no, there's a lot of space, so not everything is just gonna hit each other, so it'll probably be just like really bright and chill. I like that. I don't know if we'll still be around then, probably not, but it's fun to think about. Okay. Oh, and that was apparently the end of a section. Not the section. We've got two more. Yeah, it's very likely there's going to be like no star collision just because, and that's the crazy thing too, is like there's so many stars, but there's also so much space. And it kind of blows your minds. You know, it blows my mind at least. I don't know if it blows your guys' minds, but like that there's just so much empty space that there are these like, you know, so many of these large objects, and yet they'll probably all miss each other. Crazy. Okay, so the universe is a black hole. Is the universe a black hole? There are some superficial similarities. The mass and radius of the observable universe fit the same relationship defined by the mass and Schwarzschild radius of a black hole. And the universe has an event horizon, which is the boundary between galaxies we can see and galaxies we can't see, because their light hasn't had time to reach us in the age of the universe. There are also real differences. At a trivial level, a black hole has an inside, the sealed-off space and time inside the event horizon, and an outside. The universe is defined as all space and time, so it has no outside. Also, the event horizon of a black hole is a one-way barrier. While no information can escape, we could choose to pass through the event horizon and learn about what's inside. In our accelerating universe, the event horizon, at a distance of 16 billion light-years, marks events we will never see, no matter how long we wait. We might see events in galaxies that took place before they crossed the event horizon. Subsequent events are forever beyond our view. Ned Wright, an astronomy professor at UCLA, puts it succinctly in his Cosmology FAQ. Quote, "The Big Bang is really nothing like a black hole. The Big Bang is a singularity extending through all space at a single instant, while a black hole is a singularity extending through all time at a single point." End quote. Another way to say this is that our universe had a singularity in the past from which everything arose, while a black hole has a singularity into which things might disappear in the future. Black holes have also been invoked to explain the existence of the universe. This is speculative cosmology, so fasten your seatbelts. The Big Bang theory depends on an episode of inflation, a period of exponential expansion 10 to the negative 35 seconds after the Big Bang, during which the universe ballooned from a size smaller than a proton to roughly a meter across. There's some observational support for inflation, but still no good theory for what caused it. Oh, got an itch. An intriguing paper published in 2010 tried to remove the need for inflation by extending gravity theory to a new type of fundamental particles. The theory invoked a repulsive force called torsion. Torsion isn't noticeable at normal densities and temperatures, but in the conditions at the time of the Big Bang, it would have allowed a universe to form from within a black hole. Our universe, then, would be space-time spawned by a black hole. This idea has the side benefit of explaining the arrow of time. Time flows forward for us because of the time asymmetric flow of matter into the event horizon from a parent universe. That is, on the other side of the event horizon, in that parent universe, time flows in the reverse direction. This wild situation arises because the events that have occurred since the Big Bang play out in reverse in the parent universe. An even wilder theory published in 2014 reached into the toolkit of string theory. In an attempt to avoid the Big Bang singularity, researchers at the Perimeter Institute in Waterloo, Canada, proposed a theory that our universe arose as a result of the formation of a black hole in a higher dimension universe. In our three-dimensional universe, black holes have event horizons that are two-dimensional. In a four-dimensional universe, a black hole would have a three-dimensional event horizon. Niayesh Afshorty and his colleagues proposed that our universe came into being when a star in a four-dimensional universe collapsed into a black hole. The Big Bang is a mirage, a tracer of a higher dimension event. They refer to Plato's allegory of the cave to describe the situation. Quote, "Two-dimensional shadows are the only things that the prisoners have ever seen, their only reality. Their shackles have prevented them from seeing the true world, a realm with one additional dimension to the world they know. Plato's prisoners didn't understand the powers behind the sun, just as we don't understand the four-dimensional bulk universe." End of section. Saw you guys were chit-chatting. They said, Astro Curiani said it's roughly 4 billion years where the rocky planets will be engulfed. Mm-hmm. Yeah, we'll be gone. It'd be cool, though. It'd be cool to see. That's something that you could see with a simulation. That cool stuff that they definitely do. I think you, Student McLeod, I think you sent the same link because I'm getting the Andromeda collision picture again with that one. Just want to let you know. It would be a cool simulation. I don't know if any of you guys have used it's not like the simulator that is used by a lot of these high level astrophysicists and stuff. There we go. So this is there it is. That's Alan Guth. He is inflation's father, as Student McLeod said. Thank you for that. What was I saying? Can't remember. Oh, I have such a bad memory. Oh well. Yeah, so we're getting Michael did the math for Guth. Oh, okay. Oh, simulations, yes. Okay. Thank you for that. Yeah, there's this thing called Universe Sandbox. I know it's probably, let's see how much it is. I don't think it's free. It's a game on Steam, but you can probably just buy it from the website. Oh, they're hiring for a science writer and community advocate. Maybe I'll apply. Okay, it's like $30. So you can get it on Steam, or is it really only in early access? This apparently says it's in early access, but it's a very developed game already. Space Engine and Open Space. Oh, I haven't checked those out. Oh. So Space Engine's a 3D astronomy program that makes a three-dimensional planetarium. That's very cool. Is that one free? No, this one's $25. And then Open Space. The old versions are free. Okay. But yeah, so there's a few different options for like if you wanted to play around with some cool simulations that obviously, like, they're not the crazy supercomputer simulations that astrophysicists are actually using, but it's really fun. You can it at least for me, I'm very much like a visual, like, tactile learner. It gives you that, like, ability to play around with stuff and, like, really understand, like, okay, if there's a star here and a black hole here, how close, and, like, what will happen when it gets closer? What will happen if it's this distance? What happens if there are multiple stars orbiting it? What if there are planets around that star that are orbiting the black hole? Like, what's going to happen? Because they use real physics and stuff like that, and it's really interesting. So those are really fun to play around with. Esther Curiani said that open space is free. But it takes, all of these are going to take a good chunk of your computer, and they're probably like, it's something you want to do probably on a desktop or a high-powered laptop. I'm sure they have like lower spec versions, but they're usually pretty big and take a lot of computing power to run, because it's just a lot of moving parts and a lot of stuff that the computer has to do, Student McLeod said, allow people to share in the chat the links of 2 to 3 good astronomy websites. Ones we each like, we can add to our collection. That's cute. I like that. I will write that down. I will do that. So yeah, like astronomy websites, or like publications online, stuff like that. That sounds really good. Or even like podcasts and like YouTube channels, stuff like that. It's a good idea. Let me write that down. We will do that. Oh, it looks like Charlie shared one now. Oh, and thank you for that. Esther Curiani shared Open Space Project. Very cool. All right. Well, I will finish up this last section, then we will wrap it up for the day. Making black holes in the lab. Let's bring black holes down to Earth by asking this question. Do we have the power to make a black hole? Before answering this question, let's recall just how extraordinary a black hole is. Schwarzschild radius is proportional to mass. To turn the sun into a black hole, it would have to be squashed down to a radius of 3 kilometers, corresponding to a density of 20 trillion kilograms per cubic meter. Turning the Earth into a black hole would mean squishing it to the radius of 9 millimeters, a little smaller than a ping pong ball. That is an amazing density of 10 to the 24th kilograms per cubic meter. To put this in perspective, the density of a typical rock is 2,000 kilograms per cubic meter. With his fantastic strength, Superman can crush a lump of coal into a diamond, but that's just increasing the density from 900 to 3,500 kilograms per cubic meter. To reach black hole density, you'd have to compress matter by another factor of 1,000 billion. Try that, Superman. Black hole creation is far beyond our current capabilities. The Large Hadron Collider creates unprecedented energies, but it is a factor of 10 million times too weak to create black holes, even in theory. We have a figure of the Hadron Collider that I'll show while I continue reading. There it is. That's the Atlas detector at the Large Hadron Collider in Switzerland. So I'll leave that up for you guys to look at. Black hole creation... Oh, I read that part already. That didn't stop news outlets from calling it the Doomsday Machine and speculating that it might create microscopic black holes that would sink to the center of the Earth and consume the planet. A search for microscopic black holes failed, and the various doomsday scenarios were convincingly debunked. If extra dimensions exist, gravity in our universe may flow into other dimensions. I lost my mouse. Is it working? Yay! Okay, you guys can see me again. I have absolutely no idea what just happened. I have no clue. I literally just tried to switch from the Hadron Collider back to my camera, and it wouldn't let me. And then I checked my my stream manager, and it was just buffering forever. And I was like, oh no. I was looking online that I was thinking about typing the last section in the chat box. I was like, how am I going to finish this? Like, there's literally like 2 paragraphs left. Oh, man. That was really weird. I don't know what just happened. I mean, I am using is there any time limit? I don't think so. I was seeing a lot of people. I watch a few gaming streamers that will stream for like hours and hours and hours, like 5 or 6 hours. And it said that I was still streaming. It just wasn't getting my video for some reason. But like my internet didn't cut out. It's very odd. Because like I could still talk to you guys. It was weird. Anyway. We're gonna finish this off. Because I don't want that to happen again. So, thank you guys all for sticking around. I appreciate that. Okay. So I think we were right after the, doomsday machine stuff. So, if extra dimensions exist, gravity in our universe may flow into other dimensions. That would explain why gravity is such a weak force. Also, since the energy required to make a microscopic black hole depends on the number of dimensions space has, it would be easier to create microscopic black holes. Looked at in this way, the fact that particle accelerators can't create miniature black holes is a refutation of extra dimensions. Also, energy sufficient to create microscopic black holes, far beyond the capabilities of the Large Hadron Collider, are seen in cosmic rays from space every few months. Yet there's no evidence that cosmic rays create black holes. Finally, even if the collider could create black holes, they'd be so tiny, 10 to the negative 23 kilograms, that they would require 3 trillion years to consume enough matter to grow to a kilogram. But if black hole theory is correct, they'd never get a chance to grow because they'd fizz away to nothing by Hawking radiation in a tiny fraction of a second. If miniature black holes could ever be made, they would offer a compelling means to travel to the stars. Interstellar travel is stuck in the starting blocks because we use chemical energy for our rockets. This inefficient fuel is adequate for getting people into Earth orbit and payloads around the solar system, but hopeless for traveling the trillions of miles to even the nearest stars. However, the energy emitted by Hawking radiation from a microscopic black hole could propel a starship to a significant fraction of the speed of light. A black hole used for space travel would have to be small enough to manufacture, have a mass similar to that of a starship, and live long enough to be useful. A black hole weighing 500,000 tons would fit the bill. It would have a size of 10 to the negative 18 meters, a power output of 10 to the 17 watts, a lifetime of 3 or 4 years, and, assuming 10% conversion to kinetic energy, would accelerate a starship to 10% of the speed of light in 200 days. The black hole would be located at the focal point of a parabolic reflector to create forward thrust. That's the concept. The rest is just engineering. And that is the end of the chapter. I can't believe it cut out literally like I've been live for 4 minutes. It cut out 4 minutes before we could finish. That's so funny. Well, thank you guys again for all sticking around. Through the technical difficulties. I am using a new program called Streamlabs, and I've heard some people hate Streamlabs, so maybe it was just Streamlabs being annoying. I hope it doesn't hear me and shut me down again. Oh, thank you for the subscription, Chips and Churros. I love your name. Thank you so much. I really appreciate that. Yeah, I was gonna say, if you guys want to subscribe or do the bit thing, we are going to do that drawing for the signed book by Chris, and I think you get to pick at least from a few different books, because I don't know if he has all copies of his books, but it definitely has a bunch. Oh yeah, thanks for the little emote too, Chips and Churros. I guess every time somebody subscribes, we get like a new emote or something like that, or like at least during December. I'm not actually sure if it works like that, but yeah, if you guys want to subscribe, we would really appreciate it. And also it would enter you into the book drawing. Also, thank you for being here. Thank you. I appreciate the thank you for the thank you is what I'm trying to say. Chips and Churros. Glad you're enjoying it. But yeah, so you can do the bits or the subs, and that will enter you into are drawing. But I think that's pretty much it for today. I think the only thing I was going to say is Wednesday, like I said, we have our regular stream with Michael and I. We're going to be, I guess we're going to just be talking about the stuff that you guys suggested, because I'm very interested in all the things you suggested. So I will be looking into that stuff. Michael will be joining us for a little bit, but like I said, he has to go study for some finals. I think we're going to be doing that stream earlier in the day too. Probably let me see if Michael will respond to my message really quickly, because I would love to give you guys an actual time for when that's happening. Probably the Q&A this week with Professor Impey, that's going to be on YouTube, and it will be, let's see, that should already be listed on the channel. Let's see where it is. Show me the live session. It's not listed. Okay. I am not sure, actually, when that's going to be. I usually get an email about that, but I don't know if it's come in yet. Let me check. Because Chris's schedule, again, is like very confusing. I can message Matthew about that as well. Let's see how long it takes for them to respond. But yeah, I think Wednesday's going to be sometime in the morning. Probably maybe like 11 my time. I think that would probably work for both of us. Matthew's messaging me back, so we should know when Chris's stream is in the next minute or two. But yeah, it'll be probably, I'd say, around 11. It's like an hour earlier than now. On Wednesday, and yeah, we'll be announcing the winner of the raffle, and talking about some of this cool stuff, so like Lunar Landing, Martian descents, Starship SN8. I'll find some ISS space photos for you guys. We'll have a good time. We'll hang out. I'm going to be running most of that stream, so it'll be kind of like this, where it's chill and fun and cool. And then Friday, we don't have our regular amateur astronomy. And then our schedule might change a little bit for the week of Christmas, because I think everyone else is on break. So I'll probably be doing my regular stuff. I'll probably be doing our regular book chat throughout the Christmas vacation, because I'm not doing anything else and I have a good time with this. So I'll continue doing that. I don't think we're doing anything else really. Professor Impey might have one more Q&A next week, right before Christmas. But we will have to see. And you should get a notification for all of that. Yes. As soon as I find out when this stuff actually is, I'll be sure to put it on the Twitch schedule. Oh, do you get reminder emails from Twitch? That's really cool. I know that Matthew sends out reminder emails for Professor Impey's stuff. Okay, he just messaged me back and said they haven't scheduled anything yet. So he's not sure either. But as soon as they find out, I will put it in the Discord. And also, if you guys aren't on the Discord, let me share that with you as well. So we try, because sometimes Twitch notifications aren't always reliable, but I try to always put when we're going live, wherever we're going live, in that Discord. So if you want to follow that, and you can also turn on so Discord is essentially, it's like a chatting network thing, where you can download, it's either an app or you can do it through just Safari or like Chrome or something, or you can download it as an application to the computer. It's totally free, and it's essentially just a community where people can chat. A lot of people use it for like playing games with friends and stuff. Like that's how I found it, But we also made a community with, it's called Astropedia, because that's what like the original whole thing was called, Astropedia. But there's like over 1,000 people on there now, and everyone just talks about like fun space stuff. And we say when we're going live. And yeah, I try to put those notifications out when we do go live. Yeah, like Salvasari said, lots of like-minded people. It's really cool. It's been really cool to see the channel grow too. Like we started out with like 250 or 300 people. It's the same one as the Coursera course. I think a lot of people found the Discord because they're part of the Coursera course. I don't know if there might be a section on there. Because there's like different chat sections. But yeah, it's essentially for the Coursera course and for this. I don't know if there's one specifically about the courses. Like a channel within the community. I don't think there is. Maybe I'll make one. For like course questions. But yeah, it's for everyone from the courses, from Twitch, from YouTube. Not from any of them, that just wants to talk about astronomy. And yeah, it's a nice little community. So I guess I will end it there. Thank you guys all for hanging out. Thank you to Chips and Churros for subscribing, and Virtual Assistant for cheering those bits. Thank you for hanging out through the technical difficulties. Don't forget about the raffle. Enter that. If you want that link one more time, I'll give it to you guys if you need it, for that explainer video about how to connect your Prime to get that free sub. There you go. And I think that's it. So, how do you enter the raffle? You just have to be a subscriber or be one of the top bit donors of the month. So right now it's Asus Hammer, Virtual Assistant, and add them all together. I still don't know if Virtual Assistant is a real person, but I guess we'll find out if they win the raffle and then tell me they're not a real person. But we'll see. But yeah, if you're a subscriber or if you're a bit donor, one of those top three, then yeah, you're a Prime subscriber, so you're all good. You're already entered. Yeah, great. So thank you guys all again for hanging out, and I will see you all on Wednesday. Have a good Monday.